Okay, let's talk about ionic equations. So an ionic equation is just another chemical equation, okay? So it's representing a chemical reaction. There's really three different types of chemical equations we could write, and two of them are ionic equations. Um, and so the first one is not an ionic equation. So the first one I have on the list is the typical chemical equation that we would write that represents a reaction. And so we would normally just call it the chemical equation. But if you want to get more specific, you could call it a molecular equation. You can call it a formula equation. But the basic idea is that this is the chemical equation with all the substances written as neutral compounds, okay? And so everything is neutral. So everything's put together how it would be if we're going to get bottles of stuff, okay? It would tell us exactly what substances we put together. Whereas we could write it in an ionic form called the complete ionic equation, and that you can also call it the total ionic equation or simply the ionic equation, which is a little sloppy because there's more than one. I'd call it the complete ionic equation. That's the most specific, clear name, I believe. And so that equation, as the name, suggests, it contains ions, okay? And the reason is because each substance is going to be written as the majority of it exists in solution. So remember, when some things dissolve in water, some things stay as a neutral compound, but some things break up into ions, okay? So the things that do break up into ions, at least when the majority breaks up into ions, they would be rewritten as ions, okay? Whereas things that stay neutral or most of it stays intact as a neutral compound, those things we would write just as a neutral compound. So this is almost like an extension of a molecular equation. You take your molecular equation and you convert it to a complete ionic. And then the complete ionic equation, that can be kind of lengthy if you split everything that breaks into ions. And so it can be a little more information than we need. So sometimes we simplify it into what we would call a net ionic equation. So a net ionic equation only includes what's actually participating in the reaction. So the things that are actually undergoing a change, okay? So when you have reactions that are occurring in solution, some things break up into ions, but some of those ions just float around and do nothing. And so if those ions just do nothing and they're just floating around in solution, then we can kind of ignore them. They don't really matter. They are present, but they're not doing it. And so those things we eliminate from the reaction. And so those things that we would eliminate, the things that aren't participating, those are called spectator ions. Okay. So essentially they're just sitting around watching other things happen. Okay. And so we sometimes just get rid of them from the reaction altogether so we can focus on the things that are reacting. So now let's go back to this, taking the molecular equation and converting it to the complete ionic, because that is probably the trickiest part. And so to determine that, you need to know what exists majorly as ions, okay? So that you can split those things up. And how you determine that is based on electrolytes. So you've got to remember what it means for something to be an electrolyte, and you have to be able to identify is something a strong, weak, or non-electrolyte. So let's review that. So strong electrolytes are things that exist as ions in solution. Okay, or at least the majority of it does. And so that's something that you put into water and it breaks up into ions either completely or almost 100% into ions. That would include soluble salts, strong acids, and strong bases. Okay, so whether or not something's a soluble salt, you determine based on, is it written down as an aqueous ionic compound, or you look at solubility rules. Okay, whether or not something's a strong acid or a strong base, that's something you basically have to memorize or have a list. Okay, there's only a few strong acids and a few strong bases. When I say a few, maybe I should say a little bit more than that. There's about 7 of each, maybe 7 strong acids and 8 strong bases. So when we look a little closer at acids and bases, I'll give you lists of those. But you can look them up as well. And sometimes you're just directly told this is a strong acid or a strong base. Any of those things that are in your molecular equation, you would rewrite those things as ions. And everything else you would actually leave as is, because everything else either is a weak electrolyte or a non-electrolyte. And the weak electrolytes exist mainly as compounds. So a weak electrolyte, when you put that substance into water, it does produce some ions, so it does split up some, but the majority remains together. So we represent what the majority is, so we leave it as the neutral compound. And that would include anything that is an insoluble salt. So when you see things in your molecular equation labeled as solid, or if you look up in the solubility rules and it's insoluble, then those you leave together. If it's a weak acid or a weak base, the majority remains intact, so you leave it together. And then the last electrolyte is the non-electrolytes, and those exist as neutral compounds. In solution, that would be any non-acidic or non-basic covalent compound. And so those just stay together in solution. So the only thing you're really changing from a molecular equation to complete ionic is anything that is a strong electrolyte, you're splitting into the ions. And then to go from the complete ionic to the net ionic, you just look at both sides of your complete ionic equation, and anything that is exactly the same, you would eliminate, okay? Because anything that is exactly the same on the reactant product side, those are spectators. And so you would remove them if you want to create the net ionic equation. So let's look at some examples. Sometimes that's a little helpful because the words may not make sense till you see it put into practice. So let's look at some examples. So here I've got a reaction. It's written in the molecular form. So this is the molecular equation, okay, or the regular chemical equation for the reaction between lithium sulfide and magnesium sulfate. And I want you to write the complete ionic equation, and then identify the spectator ions, and then lastly, write the net ionic equation. So first, what you should really do is identify the strong electrolytes, or just identify what type of electrolyte everything is. So I'm going to go through and do that. So this first compound, that is an ionic compound or a salt, right? Because it's a metal and non-metal. And I also know it's soluble. And the reason I know it's soluble is because the phase is already given to me. Okay, so if it's a soluble salt, that means it has to be a strong electrolyte. Okay, and then the next one, the magnesium sulfate, that's another salt or an ionic compound. And that is also soluble because it's already listed as aqueous, right? I don't even have to look it up, meaning that also is a strong electrolyte. Okay. And then this one, the lithium sulfate, that's also an ionic compound or a salt. It's also listed as aqueous, so it must be soluble. And so that means it's a strong electrolyte. And then the last one, the magnesium sulfide, that's also an ionic compound or a salt. And it's listed as a solid. That must mean that it is insoluble. And if it's insoluble, that means it is a weak electrolyte. Okay. So now I want to write my complete ionic equation. And the only thing I'm going to change are the things that are strong electrolytes, okay? And that would be these first three, right? So those I need to split up into ions. So Li2S, ions that is Li plus and S2 minus. But I'm going to write the entire chemical equation and I want to keep it balanced. So when I split that up, I get 2 Li pluses and 1 S2 minus. So I'll put a coefficient of 2 with the lithium, okay? Because I need 2 of those. And that is going to be aqueous just like the compound. When you split it up, those ions are still aqueous. And so that's that first compound. Now the second one, MgSO4, splits into Mg2 plus, and that is still aqueous, and SO4 2 minus. That's still aqueous. Okay. And then my products, I have lithium sulfate's going to break up because it's a strong electrolyte. And so that splits into Li plus and SO4 2 minus. But again, we want to keep this balanced, and when you split up an Li2SO4, you actually get 2 of those Li pluses, and that's going to be aqueous. And then the SO4 2 minus is also still aqueous. Any of that stuff you break apart is always going to be aqueous, so all of your ions are aqueous. And then the magnesium sulfide is a weak electrolyte, so that the majority stays together, so we write it that way as MgS. So we leave it as is. The only thing that changes from the molecular to the ionic equation or the complete ionic equation is the strong electrolytes. Those get split into ions. And then next up, we want to identify the spectator ions. And that's the things that stay the same on both sides, the things that have not changed, okay? And so that would be here we've got the lithium ions. We have 2 lithium ions, 2 lithium ions. Those must be spectators. And then let's see, what else? We have SO4 2 minus and SO4 2 minus. And so all of that stuff is the exact same on the reactant side and the product side. So these are all spectator ions. And now if we just, let's go back a second here. If we just cancel all those out or erase them, cross them out, whatever remains is the net ionic. So the net ionic would be S2 minus aqueous plus Mg2 plus aqueous forming MgS solid. Okay, so this here is my complete ionic equation. And then this is my net ionic equation. So the complete ionic contains everything, spectators and everything. The net ionic only contains the things that are changing. So the sulfide is S2 minus to start with, and at the end it's in the compound. It is actually attached to the magnesium in the end. Okay, so let's do another couple examples. So this next one, I want to do the same thing. Write the complete ionic equation, identify spectator ions, and write the net ionic. So just like the other one, you want to identify the strong electrolytes. The easiest way is to think about what kind of compound you have. So this first one, that's an acid. Okay, this is an acid, and you need to know if it's strong or weak. Now, that's something, if you don't know which acids are strong, then you'd have to look up a list of strong acids. And this is a strong acid. So since that is a strong acid, that means it is a strong electrolyte. Okay. And then we have the NaOH, that's a base. And if you don't know the strong bases, you can look them up. And this is a strong base. So that means it is a strong electrolyte. And then we have Na2SO4. That's an ionic compound or a salt. And it's aqueous, so that must be a soluble salt. And so that means that is a strong electrolyte. And then we have H2O. That is a covalent compound. And it's not, oops, I skipped part of the word there. It's covalent. And so that it's not an acid or base. It's just a covalent compound. So that is a non-electrolyte. And so all of these things that are strong electrolytes in this, we need to split up into ions. So those are the things we're going to change. The H2O we will just carry down. Okay, so H2SO4, when that splits into ions, we get two H pluses. Okay, and those are aqueous because all of the ions are going to be aqueous. And we have an SO4 2 minus. Right, because the cation's H plus, the anion's SO4 2 minus, and based on the formula, we have two H pluses for every one SO4 2 minus. And so we carry that 2 as a coefficient to keep our reaction balanced. And then we have the NaOH, and so that splits up into Na plus and OH minus. But if we pay attention to our balancings, because we want to keep it balanced, it's already balanced. There's a 2 in front of that, meaning there's 2 NaOHs. So for each one, we get an Na plus, so we must have 2 Na pluses. And for each NaOH, we get 1 OH minus, so there must be 2, since we're splitting apart 2 of those. And then we've got Na2SO4, so that gives you 2 Na pluses and an SO4 2 minus. And then, let's see, the H2O is a non-electrolyte, so that just stays as H2O. And so that's our complete ionic equation. And then we can identify our spectators. And our spectators, the things that stay the same, that do not change from reactants to products, that would include this Na plus and the SO4 2 minus. So all of these things are our spectators. So to get the net ionic reaction, we just remove those. And so my complete ionic would just be my net ionic from my complete ionic, my net ionic would be 2H plus 2 OH minus going to 2H2O. Now this one's a little bit unusual because now that we've eliminated the spectators, now we have excess balancing here, right? We have 2 to 2 to 2. We can actually reduce those coefficients. Usually people would drop those, reduce it down to its lowest ratio. Having the 2's in front, it's kind of correct, but it's better to report it in the reduced form. That's the more proper way. Okay, let's do one more of these. So this last one, I've got NaOH, and we're going to identify that that's a base. Okay, and specifically that is a strong base. Again, acids and bases, if you don't know which ones are strong, you look up a list of them, okay? And then, so if that's a strong base, it is a strong electrolyte. And then we have acetic acid. It's an acid. And that specifically is a weak acid. And so that is a weak electrolyte. And then we have sodium acetate. That's a salt or an ionic compound. Specifically, it is soluble, and that you can determine because it's listed as aqueous. And then that must be then a strong electrolyte. And then we have water, and that's a covalent compound, just purely covalent, and so that's a non-electrolyte. So now what we need to do is we need to break up the strong electrolytes, okay? So there's a strong electrolyte, there's strong electrolyte. So only those two. The others we will carry down as is. So the NaOH we break up, so we get Na plus aqueous and OH minus aqueous. And then the acetic acid we leave as is, so it's HC2H3O2 aqueous. Because it's a weak acid, it's a weak electrolyte, and the majority stays together. So that's how we write it. And then the sodium acetate, that's soluble, so we write it as the ions, Na plus aqueous, and C2H3O2 minus aqueous. And then the water, since it's a non-electrolyte, we leave it together as H2O. And then we identify our spectators. Our spectators here would be what? Na plus, right? And any others? No. So these are our spectators, just the Na plus. Okay. The OH minus is not, because it's OH minus on one side and it's part of water in the other. And then the acetic acid is not still acetic acid on the other side, and the acetate ion is not acetate ion on the other side. Okay, so our net ionic equation in this case would be OH minus plus HC2H3O2 aqueous going to C2H3O2 minus aqueous plus H2O. Like, oh, there we go. And so that would be our net ionic equation. Okay, so hopefully those examples helped you to understand a little bit better what we mean by molecular equation, complete ionic equation, and net ionic equation.